Okay, hi again, and this is the Chipmaster, and today I'm having a laptop repair again of a HP. There's nothing written on it. I got it directly from the owner, and he said that it's turning on, but there's no image or any display on the screen. Yeah, so he said he wanted to repair it, and if I can put some urgency on it as well. So as you can see, it's a HP ELITEBOOK. It's an ELITEBOOK. You know these type of laptops. Very beautiful. Right? It's an ELITEBOOK, and it's a 8th gen CPU, I think. It is an i5 8th generation. Yeah. It's an i5 8th gen CPU. And the fault, no display, he said. I haven't done anything on, no checking, no prior checking. As you all know, I do my repairs on spot. I don't do a prior check before. So I'm doing this on the spot now. I don't know what's wrong with it. So I'm just doing it with you. Alright, so let's head over to the camera. Yes, so I'm going to plug in the power. My throat is a bit misty. Alright, so I'm plugging in the power now. It uses Type C as well. As you can see, the current there is fluctuating a bit. Alright. Yes, I get a light flashing at the side. As you can see, there's a light flashing there. Okay. Let me press the switch. Not getting anything. Oh yes, it's on. What? Let me get some more length on this. The wire is a bit shorty. Alright, so I'm pressing the switch, as you all see. Let me go to the first one. Alright, so I'm pressing the switch, as you can see. I'm pressing the switch, but I'm not getting anything. And there's a light flashing at the back. Let me try another charger. But this charger should be able to turn, my DC power supply should be able to turn on this unit. Let me get another charger. Let me get the original charger. Original HP charger, and see what happens. Oh, here it is. All right. Same light. As you can see, I'm getting the same light there. It's flashing. And it's doing the same exact thing. See, that caps lock is flashing there. I'm pressing the switch, but I'm not getting anything. So it wasn't my DC power supply. So the The laptop is actually not turning on. I thought it was turning on because it said that it turns on. Oh, so he thought it was on, but he keeps on getting that caps lock light. That's the problem. He keeps on getting the caps lock light, so he thought it was on, but it's actually not on. I think it's a battery pull. Do you think so? Do you think if I remove the main battery it will turn on? Let's try. Alright, so I'm going to take apart the unit, just the back cover, and remove the battery. I'm going to remove the battery. Alright. Alright, so here's the main battery. So I'm going to remove the battery and see if it works. Alright, see? There we go. I know this model. I know this model. Alright, so let me see if I get anything now after removing the battery. Still didn't work. And the caps lock light is still solid white. Before I take apart the computer, let's do some visual inspection. Right, this is one of the methods of repairing by visual. We have feeling, we have our touching, right? We have reasoning, and we have measurement. So those are the different methods of repairing. Alright, so this is the standby section, I should believe. Not sure. Alright, I think this is a 4-switch boost regulator circuit here. Right, so it uses a PWM step down for the common point voltage. Instead of 19 volts, it maybe uses 8 to 12 volts. Right, so this is the charging section here. As you can see, we have 4 MOSFET and a coil. Right, and this is used to buck and it used to boost. Alright, so let's check down here down the RAM supply section and the 1.8 volt section, and that's all good too. As you can see, no issues. Alright, so it still didn't turn on after doing the battery pull. Alright, so we have section here maybe for the CPU core supply or for the integrated graphics. Yes, it's a 8th gen, so this is the CPU core. These are for the CPU core supplies, and they are all looking good. So I don't see anything like liquid damage or any spill on the board. So I'm going to continue the disassembly. We have a lot of connections and screws here. I'm wondering if I should pause and remove. I'm going to pause. Oh, before I removed the wrong battery. This is the CMOS battery. I thought the CMOS battery power came from the main battery. So I'm going to remove the RTC battery. I removed the wrong battery. I'm going to connect back the screen and camera connections. Plug in the power. As you can see, the current is jumping from 20 milliamp and going back to 0 to 1, 10. See, as you can see. Anybody can tell me what this indicates? It's in a light. It's in a cycle. It's looping the current, as you can see. So it's from 1, from 10 to about 20 something, and then back to 0. And I'm pressing the switch, and as you can see, I'm pressing the switch. Right? The caps lock is solid white there, as you can see. Nothing changed. Alright, so I will have to disassemble. So this is not it's not a display issue. He thought it was on because he's seen the caps lock. And this laptop was already disassembled by someone because I'm seeing incorrect screws. So this laptop was already checked by someone. Yeah. Alright, so I'm gonna pause again. Should I? No, I'm not gonna pause. I can use this as a disassembly video as well, for persons who want to learn how to disassemble one of these laptops. Alright, I'm removing this cover shield. Oh, this keyboard can be removed as well, so we have more screws under the keyboard. It's tight. So we have this screw. I believe that's for the keyboard. And this one here, yes, KB. That's for the keyboard. I should be able to remove the keyboard now. Yes. Alright, so the keyboard is out. And I have a lot of screws under here. Removing the heatsink and fan. It's a bit fun. Feeling tight. I'll have to pause because this part is a bit tight here. Oh, maybe there's another screw hole in the board. Indeed. That was my problem. Now the board is easily out. Damn. Alright, the board is out finally. Yeah, here we go, boy. Alright, so I'm checking on this side of the board. And I don't see anything so far. Alright, this is the Thunderbolt chip from by Intel. Right, for expansion. Right, PCI Express for high speed. So this is similar to a redriver, which can which can accelerate and it can process data signals at the same time, right? And that is most likely done in the display part. This is like a PCI Express driven device, right? Thunderbolt, high speed frequency of data transfer. All right, this is the embedded controller. All right, new button. This section is also good. All good, all good. There's no problem there. The audio section here. All right, this is the audio, and it's good. All right, CPU core supply section. This is the CPU PWM. It's an ISL 9585 9A, and that's good. No problem there. So I don't see any corrosion, any burn, any explosion on the board. So I'm going to do my next method of repairing, which is the diode checking. Right, so we're going to check for shorting or stuff like that. Okay, so I'm going to check now for shorting. For any short or any abnormal values. Alright, so I'm going to start off. This should be 3 volt and 5 volt section. I get 140. Hold on. Oh, I see. Alright, so let's check this coil. We get 415, 418 on that coil. This one should be for the RAM. This is not looking right. This is not looking right. 97. Oh, it's for the RAM. Yes, this is RAM supply. My probe was touching the ground pin of the connector. Yes, that's for the RAM. And this is most likely, this is VCC IO. And this should be VCC SA. Oh, we have a short here. We have a short. This is most likely 5 volts. What? Did I just get a short reading a while ago? So what the hell was going on here? Oh, it's okay. That could swear I got a short there. 316. So this is 3 volts. This should be 5 volts. This is 1.8 volts. This is RAM supply. I know that for a fact. Yes, that's for the memory. PWM. Alright, that's good. The common point. That's good. 370, 380. So there's no obvious short. Or the port is soldered to the board. Right, so I give power. Remove the fan. I don't need it at the moment. The fan is not necessary at the moment, so I'm going to check some voltages now. Alright, so I'm checking here. I have 5 volts, that was correct. And this should be 3.3 volts. This one is 3.3, sorry. Yeah, I have 3.3 volts here. And this is 1.0 volts, and I should have 1.8 volts here. Oh, the board is on! The board is on. You see that? I get 2.5 volts. This is for the VPP voltage for the RAM. Am I getting 1.0 volts? No 1.0 volts. VCC SA is there? Yes, I'm getting VCC SA. So the board is triggered. Right, so I have to check. Let me turn on back the lights. So the board is triggered. Oh, as you can see, I now have 10 milliamp. As you can see, I now have 100 milliamp. I wasn't getting that before. So it is actually on. Interesting. So I get 2.5 volts. So I'm going to check and see if I get 1.2 volts for the RAM. So based on what I'm seeing, that the CPU has already released SLPS4, because once all the working conditions for the standby voltage, there are 11 to 12 working conditions for the Intel Series 6 all the way up to Intel Series 10, which is the Comet Lake. They have 11 basic working conditions. So we have VCC RTC, right? We have RTC reset, SRTC reset, 32.768 kilohertz. Then you have VCC DSW 3.3 volts for the deep sleep well. Then you have DSW power OK, right? And then after you have VCC PRIM 3.3, VCC PRIM 1.0, VCC PRIM 1.8, and then after that, then you have RSM reset, and then you have lastly the power button. So that's 11 working conditions for Intel Series 6 up to the 10th generation, right? So my observation on this board now, it's turned on. So I'm going to check if I'm getting 1.2 volts, right? I already see that I'm getting VPP 2.5, which is for the RAM, right? And I'm going to check if I'm getting 1.2 volts now. Right, 1.2 volts should be here. Yes, I get 1.2 volts. So the board is actually on, right? So it is triggered. So it's the owner, the customer is correct. Let's check the common point. That should be 12 or 8 or 13 volts, I believe. 12 volts. Excellent. So I was correct. So the common point for this board is 12 volts. So instead of 19 volts, as you can see, I now get an orange light. Right? I wasn't getting that. I wasn't getting this current, as you can see on the screen here. Alright, so as you see, I'm getting the orange light. It flashes white, orange, and then the board triggers. As you can see, I get 100 milliamp there of current. All right, so I get VCC SA. So I'm going to check if I'm getting secondary 3 and secondary 5 volts. So we're going by the timing. So for the 8th generation timing, right, SLPS4, right, we have this coil here, right? This should be VCC IO. Let me check. So we have 5 volts, so we have 5 volts, 1.2 volts, 2.5 volts, right? We have 3.3, we have 1.0 volts, VCC PRIM 1.0, right? I now should check, I have VCC SA here, right? So this should be VCC IO 0.95 volts, right? So let me check. This is the order in which you have to check for the Intel Series 8th generation. Alright, so as you can see, the board is now on. So let's check here. I have 1.0 volts here. Alright, this is 3.3 volts, and this is 1.0 volts. So this is VCC SA, and here Yes, so I have VCC IO, all right, I have VCC SA, and here 0.95. Excellent. So I'm getting 0.95 volts, right? But I'm not getting the CPU core supply. No CPU core. No CPU core. Right? And this should be 1.8 volts. Excellent. 1.8 volts is there. Right? So let's check if we're getting clock. I have to remove the CPU. So far I have VCC IO, right? No, sorry, this is VCC PRIM 1.0, right? VCC PRIM 3.3 volts, right? VCC PRIM 1.8, right? Our VCC VCC 80 this is VCC ATS 1.8 volts. Yes, standby. I have 1.2 volts for the RAM. Oh, here I have 1.2. I have VPP 2.5 volts for the RAM as well, right? I have VCC SA, I have VCC IO, right? So I'm not getting CPU core supply. Let me check the resistance on the CPU core. I have 1, 2. Alright, so the CPU core is good. VCC GT for the graphics. Excellent. So the CPU core, I get 3 now. See? 3. VCC SA should be about 12. Alright, 11. Excellent. So there's no short. So I need to check if I'm getting secondary 3 and secondary 5 volts. Alright, this is a Quanta base board, as you can see. The board number is here. Alright, so it's a 6050A 2945601. Right, and it's a pretty common motherboard. Alright, so I need to find secondary 3 and secondary 5 volts. I will need a these normally use a 6-legged MOSFET N channel. Oh, we don't. So let me check. I think I found it. Secondary 3, secondary 5. 472 there. 476 rather. And here have 500. Alright, so I'm going to go under the microscope because I want to see properly. Alright, so this is the chip. Alright, so as you all know, pin number 1 is the input. Pin number 1 and 2 input. We have 407, right? Pin number 4, which is the bias, which is the power supply. We have 400. Pin number 3, which is SLPS 3, which is the enable, right? And I have another enable here on pin number 5, right? And pin number 6 and 7, which is the another input, and the output of this side is here. Alright, so let's check if we're getting inputs and then outputs and enables. Alright. Oops, I'm on diode. Alright, so the input here is 5 volts and the other input here is 5 volts. Okay, so this is 5 volts output and I'm getting 5 volts output. Excellent. On both sides, and this should give me 3.3 volts for the enable. Excellent. The other 3.3 volts. Excellent. Oh, I wasn't under the camera. Sorry about that. Alright, so let me check again for 5 volts here. Right, the other end is 5 volts. 5 volts here. Alright, the output also 5.2 volts on the other output, 5.2 volts, and the enables, which is 3.3 volts each, which is controlled by SLPS3. Here it is, and then pin number 5, another 3.3 volts. So that is good. So I need to find one for 3.3 volts now. Should be up here. Oh, here it is. Here it is. Alright, so first I'm going to measure the resistance. Alright, so this coil, so this is our integrated MOSFET. Two MOSFETs with a switch. Alright, the output, I get 3.350, and the other one, I get 272, 275. I'm going to plug in the power now. Alright, so I'm checking the output. I get 3.3, 3.3, no problem there. Input is there, 3.3, and the other input 3.3, and the enables are there. Yes, both enables are there. Now I'm going to check for the clock. Guys, I'm checking the resistance on the clock. This is a 24 megahertz clock. Crystal. Should get 720 on one side, 792 on the other side, 795. So it's good. Alright, so I'm gonna go back under the microscope and check the voltage for the clock. Here is the crystal. Right, so as you can see, H24 indicating that it's a 24 megahertz clock. Alright, waiting for it to turn on. It's not turning on. Oh, yes, it's lighting up. Yes, there we go. We have 100 milliamp. Alright, checking. Alright, so I get 0.4 volts on one side. On the other side, 0.46. Check again the other side. 0.39 on the other side. 0.46. One more time. So the clock is working. The crystal is okay. So there's no CPU power supply. No CPU core supply. Alright, so I will see if I can find a data sheet. Just looking under here. Oh, this is for the Thunder. We have another RAM chip here for the Thunderbolt. Alright, that's a Thunderbolt BIOS RAM chip. And this is the main BIOS, as you can see there. So I'm getting all the main supplies except for CPU core. I'm plugging in the power again. I want to check here on this pad here. This pad. Oh, it's 5 volts, and this one. Oh, it's just 5 volts output. Sorry. Yeah, from the coil. So all the rails are present so far, as I said before, except for the CPU core. Alright, this is the 0.9, already checked. Sometimes the BIOS can cause this problem, right? Because the ME firmware needs to be configured on the clock module. I can't check the clock module because, yes, to a point, yeah, on the LAN, I think. Yeah, this is the LAN chip. Here's the LAN. Okay, here's the LAN, and it's a Intel based LAN here, original LAN card. Let me check the resistance. Alright, that's good. Crystal is good. 730. I'll have to see if I can find a schematic. I don't want to flash the BIOS. I want to properly check. Some guys would immediately go and flash the BIOS. So I need to check the CPU power supply working conditions first. VR on, the main supplies. Right, I have to check with oscilloscope to see if I have any over voltage or over current protection. And it shut down the CPU core supply. So it's an ISL 9585. So I'm going to check for a schematic first, if I can find. If not, then I'll use a datasheet to confirm the working conditions of this CPU power supply chip here. Okay, so I have here a datasheet. Instead, this one is C. I could not find a A. As you can see, it's a 1 plus 2 plus 1, meaning that there's two CPU cores, one for the VCC SA and one for the integrated graphics, right? So that's what this means. These are the phases. So it's a 1 plus 2 plus 1 voltage regulator with expanded, right, integrated clock control max register, which is ranging support from Intel IMVP8, CFL and CNL CPUs, right? Coffee Lakes and Cannon Lakes. IMVP stands for Intel Mobile Voltage Positioning, and the version is 8, which is a specification from Intel, right? So this CPU power supply chip is designed specifically for Intel CPUs only, not AMD's. Please bear that in mind. As you can see, it's for the Coffee Lake, which is the 8th gen, or you can use the Cannon Lake CPUs, right? So these are the abbreviations, right? So it's an ISL 95859C, right? Provide a complete power solution for Intel microprocessor supporting core, graphics, and system agent, which is the VCC SA. So I said before, 2 for the core, 1 for VCC SA, and 1 for the integrated graphics, as you can see here, right? So we have supporting the core, which is 1, 2, 1 graphics, and 1 system agent, or you can call it VCC SA, which is the sustained voltage for the Intel CPUs, right? So, and it's compliant with Intel IMVP8, as you can see, trademark, which is trademarked originally by Intel. The controller provides control and protection for 3 voltage regulator, right? The VRA and VRC output support 1. So it's correct. So this CPU power supply, as you can see here, let me go back over to the microscope. Right, so we have 1, 2, which is 2 plus 1 plus 1. So we have 2 cores, 1 VCC SA, the system agent or the sustained voltage, and this is for the integrated graphics. Right, so it is correct. So let me go back to the... Alright, so I'm interested in the pinouts at the moment. Let's see if I can find a pinout here. Here is it. This is what I'm interested in. Alright, so we have VCC, and we have VIN, which is the main power supply input. This is the working mode voltage, which is the V boot voltage mode. We have prog 1 and prog 2. Connecting these two to a 10 kilo ohm resistor to ground basically switch the output voltage of the entire CPU power supply chip. So this is very important. As you can see, we have SDA. Hold on, let me pause. All right, let me pause a bit. Okay, so this is the main power supply input. This is another power supply input. This is 5 volts and this is V in. This is 12 volts for in our board. It's 12 volts for the common point. So we're going to check here. Right, we have alert, which is asserted by the CPU each time as you see the hash sign indicates that it is low. So each time the CPU needs to talk to this chip, it needs to pull alert low, and it will issue SVID clock and a SVID data. Right, so we have SDA and we have SLCK, which is I2C line, or we can call it a system management bus. Right, we have VR hot. Right, this indicates that any one of the CPU output power supply is there's some thermistor beside the coils. Remember, the coil. All right, so the coils are an unreliable component. Right, it doesn't know, it's a blind man. It doesn't know what's going on the race stage of the power supply. So it needs, the CPU power supply needs to monitor the temperature of the coils. So this is why the coils get so hot, and when they get hot, what will happen is that it will burn the MOSFET. So this is why the upper MOSFET always burn and they break. So there is no compensation. So you have to compensate for the amount of temperature, because instead of using a resistor, they use a coil, because the coil is the actual only way to provide proper voltage to the CPU, which has something called mutation, where that it stores energy and releases it as an electrical charge. Right, so this is the mutation. So the voltage cannot suddenly change between the coils and the current at the same time. So they need something to compensate, because the coil only can provide storage of current and voltage. It's like a battery. It can charge and discharge. So what it needs, compensation. So this is why it is connected to, between the coil, there's a resistor, which is for impedance. Right, there is a capacitor for differential mode filtering, and also acts as an impedance, right, and impedance matching. So the resistor is for impedance, the capacitor is for differential mode filtering and impedance matching, and there is a thermistor for temperature compensation. So those are the three things that is needed in the CPU power supply. Because of the high power delivery that the CPU demands, it has to have those components between the front end and the back end of the coil to compensate, because the coil alone cannot do all that compensation. It just provides voltage and charge and discharge. Right, so that is why it is one of those reasons for. Alright, so I'm not going to go to all these pins. Right, as you can see, we have VR hot. So any of the output of the coils are getting too hot. Right, what will happen is that each of these has an NTC. We have a NTC, which is monitoring. As you can see, NTC stands for negative thermal coefficient. We have one for B. Right, we have one for we have another yes, this is the main NTC, right, B, and we have C, and we have A. Right, we have one for A, one for B, and we have one for C. C doesn't need a NTC because of the this is for the system agent, right? This should be for the core. This should be for the graphics, right? So any of these power supplies are getting too hot. What will happen is that, let me get my pointer fix. I didn't have my pointer fix. Did I have my pointer fix? Alright, so let me pause for that one. Okay, so right, so as I said before, so this is, so any one of these temperature sections getting hot, right, for the A and the B, it will go and tell the CPU that the coils are running too hot, right? and then it will send the CPU to drop the CPU frequency. You'll see a sudden slowness in the computer at that time, and it is cooling down the MOSFETs, hence cooling down the coils, because you don't want to burn them, especially the upper MOSFET, which is switching too fast, right? So that's the working order. So I'm going to go and check all of these pins. I'm going to check pin number 33, all right, pin number 33, pin number 34, and we have an enable, all right. We have an enable. So once the VR enable is okay, so I get VCC SA, so I know I'm getting enable because I'm getting VCC SA 1.0 volts. All right, so VR enable. Once VR enable is okay, generated, it will generate the output for the VCC SA, which is on this side, and then it will release a VR ready signal to tell the embedded controller that the CPU power supply is ready, right? And it will now and should wait on the CPU after the PLT reset. Then it will start to communicate with the CPU power supply chip through the SDA and SCL and the alert to actually produce the CPU working voltage, right? So this is calibrated from the factory by Intel, and it has to work at a certain voltage curve, right? So I'm going to check, well, based on my experience, I'm getting V in and I'm already getting VCC. So I'm going to check pin number 33, 34 and pin number 40. All right, so I'm going to go back to the microscope. All right, so here we go. Alright, so pin number 33, pin number 34, pin number 40. Alright, so I give power. I await for the unit to power on. Alright, it's now on. And I will check pin number, this pin number 1. Alright, so it's pin number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so that's 10 pins on each side. Alright, so pin number 10, 20, 30, 31, 32, 33. I get 12 volts, that is the input. Next one is 5 volts. Right, this is the 5 volt coming in, as you can see, and this is acting as a shunt resistor to limit the current. That's why resistor is here, so the 5 volts come through this resistor first, right, and then it comes through here to limit the current, and it is sending that 5 volts to the chip here. This is the capacitor. Alright, so I get all of them, and let's check pin number 40 for the enable. 10, 20, 30, 40, 3.3 volts, 2.9 volts, so everything is okay. Right, let's check on the SDA SCL. That should be pulled up by 1 volts. Right, and that's for the VCC SC, and that's 35, 36 and 37. Alright, 35. So this is 10, 20, 30, 31, 32, 33, 34, 35. 1 volts. So this is VCC ST. So VCC ST and VCC STG is okay. Right, and the next one, which is 36, 37. Right, the alert doesn't need it because it's going to be pulled low at all times to assert to the CPU. So that's 30, 31, 32, 33, 34, 35, 36. Alright, and that's okay. So all the basic working conditions are fine, but I'm still not getting a CPU core. So I think it's now time for the oscilloscope. And then we're going to check with the oscilloscope to see if the CPU is actually sending SVID. Well, it won't because there's no PLT reset. After the CPU power supply, PCH port OK have to be generated. PCH port OK is generated. I don't have a schematic to check PCH port OK. My embedded controller is a BGA package, so there's no way to go under the CPU, under this BGA, to check if PCH port OK is generated. The CPU is also BGA. There's no way for me to check PCH port OK. I don't have a schematic, so I cannot check any logic circuit for PCH port OK. So that's going to be a bit daunting for me at the moment. Right? I don't think it's a bias problem. I don't think it's a bias issue. Alright, I'm just inspecting this DR MOS. That's DR MOS. That's one for the CPU. This is a dual MOSFET for VCC SA. One for the CPU here, another for the CPU core here, and one for the graphics here. Right here, these are all DR MOS chips. Right, and the CPU power supply will send a PWM signal to this chip to drive the internal upper and lower MOSFETs that's inside. You can also check that with oscilloscope. Talk. Is this a dead CPU or not? Right, if I flash the BIOS, I guarantee you there will be no change. Alright, so I will use oscilloscope to see if the CPU power supply is not actually generating the power. Alright, so I have the oscilloscope ready now. So I'm going to check on all power supplies, 5 volt, 2.5 and so on. Alright, so first I'll start off with 5, so I'm going to give power. Alright, so I'll give power now. So I want to make sure that I'm seeing full range. Here we go. Alright, so we have voltage there. Alright, 5 volt is there. Alright, this is 2.5. Waiting for it to turn on. Alright, see, 2.5 volts is there. Next I have 3.3 volts. This is 3.3 volts. Alright, so 3.3 volts came. Alright, next we have 1 volt. This is VCC ST. 1 volt is there. And this is VCC 1.0 volts, standby. There we go. We have a voltage there. This is VCC SA. Alright. There we go. We have 1 volt for VCC SA and CPU core. CPU core. No CPU core. So the chip is not being told to turn on for the SVID. Alright, so as I said before, the BIOS is the last thing I want to do. I'm just taking a look at it. As you can see, it's a Winson 8x6 package, and it's a 32 megabyte BIOS. Alright, so let me go under the microscope. A 32 megabyte BIOS, I believe. Alright, so it's a 256, so it's a 32 MB. I'm going to program it now, just to clarify, even though I'm not I doubt it's the BIOS. Alright, let me program. Okay, so I already have the file here, so I'm going to program the BIOS. So I'm using the SVOD, as you can see, selecting the 25 flash, and I'm read this socket. Let me double check if the socket is intact. Test pin false. All right. Okay, so I'm trying again. SPI read safe socket on pin 1. Okay. Okay, so now it's connected. All right, so I'm going to, I already have a backup, so I will not read. Well, I'll read because it, just in case if it works, I can copy the DMI information back to the flash file that I'm going to flash inside, and then I know I have a proper backup, so I'm going to save. I'm just going to call this backup HP ELITEBOOK. All right, just on the desktop here, because I already have a file. All right, so I'm going to open my, I can't drag. All right, so I'll browse. And this is a HP ELITEBOOK G840G3. And it's a ELITEBOOK 840, 840 G3. Is this the number? Let me confirm. It's a 6050. Oops. So it's a 6050A 5601. 5601. Oh, here is it. Oh, no. Here it is. Yes. It's a G5. It's a G5, sorry. All right. This is ME is clean by me. Backup perfectly working. This one. Oh, that's the wrong one. All right, so I will now write. This will take some while because it's a 32 megabyte BIOS, so the larger the BIOS, the longer the flash and the write time will take to program. All right, so I'm going to pause until this one is finished. Okay, so it's now programmed. As you can see, verification was successful. So I'm going to put it back inside of the socket. All right, so I'm going to put it back inside of the socket. And then see what happens from there. I doubt this will work. Alright, so it's in the socket, as you can see. I like about this board, I don't have to solder any at all. Alright, so I'm plugging in the power now. I give power. Let's take a look at the DC power supply and see if the current changes. Not getting anything. Oh. It's just flashing the light. Oh yes, the current changed. Look at that. The CPU is getting power. I'm getting 450 milliamp of current there. So my diagnosis was incorrect. Oh, sorry about that. My light fell. So I'm bright enough. The laptop is fixed. Look at that, guys. Eh, David? Eh? Yes. 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 So it was the BIOS. But I have to check it properly to confirm. So I'll have to find out the root cause, how the BIOS actually affect this. As I said, I need to check the clock. I don't have a schematic to check the clock distribution of each chips. So I have to properly check the board, and it's without a schematic. So now I will do a demonstration now to check if the CPU is sending SVID and reading the RAM, soft start, initialization, and so forth. So I'm going to do that now. Alright, so let's check all supplies with the multimeter. So the BIOS was the problem. Alright. And I also, this is a BIOS that I've cleaned the ME firmware already. So let's go to the multimeter now. Alright, so I'm getting the multimeter ready. Here we go. So I'm going to check all the voltages. Here we go. So pin number, first we have 5 volts. 5 volts is okay. Right? 2.5 volts VPP. As you can see, the current is now 330 milliamp, 400. VPP 2.5 volts is okay. Right? 1.8 volts VCC PRIM, that's okay. VCC ST 1.0 volts, that's okay. VCC IO 0.95, excellent, that's okay. Right? 3.3 volts, excellent, that is okay. VCC SA 1.0 volts, excellent. Right? Now CPU core, I get 0.69. Before I wasn't getting any voltage, right? This is 0.69, and this coil we got 0 volt because after the RAM is passed, then this voltage will come to about 100 milliseconds and then falls. Right? If you're playing a game or watching a movie, then this voltage will generate another second SVID to the CPU power supply chip. Then it will start the initialization of the graphics card. Next, I'm going to check if the CPU is actually running code. That's pin 258 on the DDR4. So I'm going to go under the microscope. Alright. So I'm going to go under the microscope now. Alright, so let's see if the CPU is running code. Alright, so that's here on this pin here. This is the DDR4. Alright, so this is pin 250. Alright, so let's go. So I'm going to turn on the oscilloscope. I'm turning off the meter. And I'm going to get the scope ready. Okay, so my oscilloscope is ready now. So I'm going to check on pin 250. There we go. Let's go. Alright, so I'm going to give power. Take a look at the screen and see what happens. Alright, so I'm giving power. Is the CPU running code or not? All right, it's turning on. Are we getting a wave? All right, let me check my settings. All right, so I'm at 10 volts per division. That is my problem. I should be at 2 volts per division. My time base should set to 500 microseconds. All right. All right, so I'm at 500 microseconds, and my edge type should set to falling edge. Right, so I didn't remember to change my settings. All right, so I'm changing my edge type now from rising to fall, right, because we are checking on the falling edge type. So we are checking on the data line, right? So I'm going to go again. All right, so I'm going to give power. There we go. As you can see, the memory has been read, right? So the CPU is initializing the soft start, and the soft start is starting. After the CPU get the reset signal, then it will send a second SVID to turn on VCC GT, which is the integrated graphics card supply, which is here, right? So this is the VCC GT. To know if the board is perfectly working well, you check this signal here, and this should generate within 100 milliseconds. So I'm going to increase my time base to 100 milliseconds, and I'm going to set my volts per division to 500 volts per division, right? 500 volts per division, 500 millivolts, sorry, per division, and my time base is set to 100 milliseconds, right? And my edge type is going to set to rising edge, right? So take a look at the screen, and I'll wait, and then the signal will come and drop after after 100 milliseconds within range, right? So I give power. All right, so it's initializing. Let's take a look. All right, the board is powering now. Now, after the RAM is read, then this voltage will rise and falls within the time frame. I think my volts per division was too high, so I need to adjust my oscilloscope settings. And I didn't capture anything, so let's go again. Let me check the settings on the oscilloscope. So my voltage is set to 500 millivolts. Right, this is the problem. So my trigger level is set to negative 320 millivolts, which it should be. Anybody can tell me? It should be the same as my volts per division. I'm going to go over a little bit by 130, so it's 630 millivolts per at the trigger level per division. All right, my time base is set to 200 milliseconds. Sorry, my time base is 200 milliseconds. I want 100 milliseconds. Let's go for a second. Or 500 milliseconds, that's enough. I just want to make sure that I have enough time. And my volts per division is 500 millivolts. And my edge type, everything is set. So let's go again. All right, right at this coil here. I'm just checking at the output filter capacitor here. All right, so I give power. Alright, so let me try it one RAM, making sure that the RAM is properly seated. Alright, so here we go. All right, let's wait. Let's wait. Wait for some time. There we go. As you can see, the voltage is asserted, and then it's off. So once that signal came, that voltage rise and falls immediately, then the display is there. right? So the display is there and the job is done. So it was the BIOS. So this is how you can check without connecting the screen accurately to check the board to see if the display is okay or not on these Intel series CPUs. Alright, so I'm going to pause, I'm going to put it back together and show you the full results and the end result of the display. Okay. Okay, so now I have assembled the laptop. Alright, so I'm plugging in the power. Alright, so let's take a look. Alright, so I'm pressing the switch. As you can see, the current there now is 700 milliamp, 1 amp, 1.2 ampere, Alright, so I'm waiting for the display. Alright, so we're at 1.8 ampere. One 1.7. One 1.6. One 1.6. I'm not seeing anything. Hold on, let me. Oh, we have backlight, and there you go, we have HP. All right, so now it's doing a upgrade in place from the HP website there, because I flashed a different version in it, so it's updating back with the backup BIOS as mismatched. And we should hopefully get some booting. I don't think there's a hard drive in it. I think the customer took out their hard drive. There's no hard drive inside, because I do remember removing a hard drive or taking out a hard drive before. So as you can see, no boot device, so the customer did take out their hard disk. Right, so it's no boot device found there. Okay, so I hope you enjoy, and I hope you learn something, and I will see you again in another video when I will repair something for you again. All right, bye.